When we're looking at graphs of functions and relations, we want to also determine what the dependent and independent variables are, and we want to state the domain and range. So again, the independent variable is x, okay, and that goes with domain. And the dependent variable is y, and that goes with range. Okay, and I'm going to write in x and y as well. Independent is x. The dependent is y. This is our input. This is our output of our functions when we talk about functions. So this is a continuous function. It looks like we have distance and time. Time is usually a continuous variable. And we need to figure out our independent and dependent variables. So our independent is going to be along the x or horizontal, and that is going to be time. The dependent is going to be the distance. Okay. And when we talk about the domain, we have to think about what are the possible domain values? What are the possible values x can take on? Now, since this is a continuous variable, we're going to use this notation. Okay, so this is called the set notation. So first of all, we're going to state the variable that the domain is taking on. It's going to take on variable x. We could also say that it's taking on the time. So we're just going to stick with x, and we'll just make sure that everything horizontal is x and everything vertical is y to keep from getting too confused. But then once we state that, we need to state the values that x can take on. Now, x can take on values from 0, and it looks like it includes 0, all the way to 6.0. Okay? And since this is continuous, we really want to state that it is continuous. So it's going to take on all real numbers versus taking on integer values or whole number values. So we show this as XER, and essentially that implies it's continuous. So the range, we're going to do the same thing. We're going to use these funny curly brackets. We're going to state our variable, draw that line. The range values are going to go from 0, and it's going to go all the way up to 30 and including 30. And since it's continuous, we're going to say that is y can take on all real numbers. So it can take on all the decimal values in between 0 and 30. Okay, so our independent and dependent. Independent goes with domain. Okay, dependent goes with range. So we can do the same thing here. This is displacement versus time. Okay, so our independent variable is going to be the time. The dependent variable is going to be along the y-axis, and that is displacement. Okay, so this is our relationship, time versus displacement. And it looks here that our domain, our possible x values, can take on values from 0.0 all the way to 10.0. So how we write that is, we write these brackets, and this is just a formal way of doing it. We don't always write these formal brackets in, but we're going to write them in for now. So that first part establishes the variable of the domain, and then we use the domain values from 0.0. So x can take on values from 0.0 to 10.0. Now, since it's continuous, we want to show that it's continuous with XER. Okay. Now, a lot of times what we've seen in the past is just this given. Okay? And that usually implies the correct answer, but this is a more formal way of doing it, and it's a more complete way of establishing our domain and range. Okay? And this is called set notation. Okay, so the range then we're going to do the same way. Y, okay, it can take on values from 0, okay, from 0 all the way up to, and it looks like it includes 16, so it's going to say y is greater than 0 and less than 16, and it is continuous, so we're going to let y be element of all real numbers. So here we're going to have our world population, our independent, okay, variables along the x, so it looks like it's the year, and our dependent variable looks like it's the population. Now, this one here, when we talk about the domain and range, it's a little bit weird in that we could possibly say that this is continuous, since the increments of time can be broken into any increments, and we can also say that the population essentially is continuous because there's so many, the differentiation between each point on that graph is different. However, we could also claim that the population is discrete, okay, and then that would make our x-axis or our time discrete as well. So in this case here, I think because of the smoothness and the fact that we really technically, although we technically could break it apart and find little gaps in between all those data points, we will simplify things and just say that, our x is going to be from, it looks like 1810. Okay, it looks like it's about, looks like 1960, looks like about 2010. Okay, and we're going to say that x is an element of real numbers, although it would be okay to say that x is an integer. Okay, so either way, whether you make x an integer, okay, the integer sign is this funny looking z, okay, or you can use I for integer as well. That would be correct, although, I don't necessarily think I would mark it wrong if you were to tell me that that is essentially continuous. Okay, so we're going to do y the same. It's going to be from 1 billion all the way up to, it looks like it's about 6.9 billion. Okay, and then we'll say that, again, x is an integer. Okay, in fact, we can even say that it's a whole number, a natural number, if we really want to be picky about this. Okay.